let's take a look at the buoyant force, and I want to show you kind of where it comes from and then how you can apply it in a very simple way. I want to try to make sure that you don't overcomplicate this concept, and we'll get down to just the main core principle and then just really see how we can use it in practice. So let's get started. All right, now when you submerge an object in water, there's a difference in pressure between the top and then the bottom of that object. And the lower you go in a fluid, the higher the pressure is. So we got more fluid pressure on this end below than we do up here at top. And that difference in pressure gives rise to this upward force that we call the buoyant force. And we won't go through and just prove all that right now, but that's the general concept of where this is coming from. And you can always calculate the buoyant force very easily on any object that is submerged. And all you have to do is take the density of the fluid, multiply that by the volume of the fluid that is displaced by the object, and then the gravitational constant here. So you can see because this object is totally submerged, it can displace a volume of fluid equal to the volume of itself. So in this example here, if we were analyzing this problem where you've got this mass on a string inside of this fluid, then the volume of the fluid that is displaced by the object would actually end up equaling the volume of the object. So we would say volume of fluid displaced equals volume of object. And you'll see how the subscripting of this becomes really important when we start solving problems. Now, this doesn't necessarily have to be true where these two things have to be equal, of course, because you can partially submerge something. So in a scenario, you can imagine just taking this string and mass and just pulling it up so maybe only like half of the volume of the object is in the water. And then that's where this, subscripting really plays an important role, because you have to figure out, well, how much fluid has been displaced. It's only half of the volume of the object, and then you have to, sub that number in here instead of the volume of the whole object if it was fully submerged. So it's critically important that you know like how much of the object is totally submerged or not. All right, so now let's get a little bit more practical in the next part. All right, so let's start with this example, and we have an object mass m. It's submerged fully under some water. It's held with a string as well, and I'm not showing where the string goes, but just assume everything's at rest. And then I've set up here that the object is 3 times as dense as the fluid. The density of the object here is 3 times as dense as the fluid. So what I want you to do is draw a free body diagram for the mass, identifying all forces, and importantly, to get the magnitude of the forces relative to each other correct. So if there's a force that you think is twice as large as another one, obviously you would indicate that as an arrow that's twice as long. So go for it and see if you can get it, and then we'll do it together. All right, so first we get the directions. Gravity's down, buoyant force is up, and tension is up. So those aren't the magnitudes quite yet. All these need to sum to 0, and let's try to get the magnitudes. So the force of gravity on the mass is just mg. However, when we're in fluids, we've learned that we can just write mass as density times volume. So we get the density of the object times the volume of the object times g. So that's the force of gravity. Notice how I'm being very specific with the subscripting there. And then for the buoyant force, it's just the density of the fluid times the volume of the fluid displaced. Always just write that out first. Don't think too hard about this. And then you can look at the subscripts again and ask the question about this term. You're always going to have the buoyant force as the density of the fluid, always. But you will be able to change this term depending on if the object is fully submerged or not. So here we see that the object is fully submerged, and so the volume of the fluid displaced is the same thing as the volume of the object. And so we can come in and write that. And now we get the buoyant force is the density of the fluid times the volume of the object times g. So go ahead now, pause the video, and compare the force of gravity in terms of magnitude to the buoyant force. And you might need some other information on the slide here to be able to do that. But give it a shot, and then we'll take a look. All right, so I just plugged in up here. We know that the density of the object is 3 times the density of the fluid. Maybe this is I don't know. Well, it's probably not a rock, but it's something that's more dense than the fluid. And if I plug that in, we've got now the same three terms. So density of fluid, volume of object times g, and then density of fluid, volume of object times g. So we can see that the force of gravity would need to be 3 times as large as the buoyant force. So up here at the top, I've drawn a free body diagram that's not correct quite yet, but it is showing that the buoyant force is about a third of the force of gravity, or the gravity force is about 3 times the buoyant force. So clearly this would cause downward acceleration. So the tension obviously pushes up and makes up the difference, and we could draw that here. And so the tension would be 2 units. The buoyant force would be 1 unit, and then the force of gravity would be 3 units, and everything's balancing out now. All right, now what's a practical application of this? Well, up here, right next to the buoyant force vector, I've just rewritten the equation. So density of fluid times volume of object times g. And just remember, it's only the volume of the object in this case, because the object is fully submerged. Remember where the buoyant force comes from. That we showed at the very beginning of the video in terms of the subscripting, volume of fluid displaced. Okay, but just look at this for a second and just think experimentally. I mean, we could set this up, right? You get some water, put it in a cup or some fluid, put it in something, and then just get some object that you can measure the volume of pretty easily, and some string. And what could you measure about the system that might be practically useful? Take a hint. It's something to do with what you're seeing up in this equation. All right, so pause the video and see if you can get it. All right, so over here, I'm showing you that you could measure experimentally the tension just with like a spring scale or something, pretty easy to do in newtons. You could calculate the force of gravity on the object because you know its mass, or you could put it on a triple beam balance, find out the mass, multiply by about 10 newtons per kilogram, get the force of gravity. So now you got that. And then with these two pieces of information, you'd be able to use Newton's second law and find the buoyant force. And you could also measure the volume of the object, assuming it was kind of a uniform object. And then you know G, and so you could figure out the density of the fluid. So maybe you have some unknown fluid down here, and with this object and a spring scale and this physics, you would be able to experimentally determine the fluid density, which is pretty cool. So a nice application. Let's write out the second law as well, just so we have that. So you can see it up here. Sum of the forces on the mass equals 0. The buoyant force magnitude is what capital B represents, is up, so it's positive. Tension, capital T, that's the magnitude of the tension, so we have positive as well, and that's an upward force. And then minus the gravitational force on the object, mg, sums to 0. And of course you could put in rho v for the density and volume of the object times g as well. But there you go, there's Newton's second law, and then you would use that here in combination with this formula, and you could find the fluid density. All right, now let's keep going, and I've got some interesting conceptual questions about the buoyant force to ask you. All right, so here's a conceptual question. We've got two scenarios, A and B, and we've got a situation where this mass is, again, held by a string, everything's at rest, and the density of A, object A, which is this mass here, is greater than the fluid. And then over in B, we have the density of object B, which is this object here, and that is less than the density of the fluid, and there's a string here. So if you cut the string, this thing would rise, and if you cut the string, this thing would sink over there. The density of A is greater than the density of B. All right, the question is a simple question, and it is compare the buoyant force on A to the buoyant force on B. Is there a larger buoyant force on one of these than the other, or do they both experience the same magnitude of buoyant force? Pause the video and give it a shot. All right, let's take a look. Try not to overcomplicate this. Again, anytime you're dealing with a situation where you've got an object that is submerged or partially submerged, there will always be a buoyant force. And just write down the formula with the right subscripts in the same way every time. Get that on the page, and then you can kind of do your conceptual reasoning in a very procedural way that helps you avoid mistakes. So, for example, immediately I know that the buoyant force on object A is the density of the fluid times the volume of how much fluid is displaced by this object, and then times g. All right, compare that over here, sorry, this B over here is for object B. That doesn't have anything to do with this B. This is for buoyant force. Sometimes people use F sub B or just capital B, and I'm just using capital B there, so just watch out. But over here, same thing. Density of fluid, and the fluids are the same on both sides, so this term is the same for both A and B. And then the volume of the fluid displaced, well, how much fluid does this one displace compared to this one? The same amount of fluid. They're both the same size objects, same volume objects. And so because they displace the same amount of fluid, this term will be the same, and then g is the same. So the answer is they both experience the same magnitude of buoyant force. So what that means is that the fluid is pushing up on both of these objects with the same amount of force. All right, let's look at one more idea here with the buoyant force. Now we have an object that is partially submerged. So it's this big object here, and there's fluid everywhere, and it's just floating. And I'm telling you a fact that the density of the object is 0.8 times the density of the fluid. And I've given a dimension for the cross-sectional area of this object, and then the height of it as well from top to bottom. And the question you have to solve is what percent of volume of the object is above the fluid level? And I've given you enough information to be able to theoretically do that. All right, so go ahead and pause the video and see if you can get that. Don't overcomplicate it. I'll give you a big hint. This is all about the buoyant force and also Newton's second law. Just apply those first principles in variables. Be very careful and diligent with your subscripting, and you should be able to get to the answer pretty easily. All right, so give it a shot and we'll take a look. All right, well, this object is at rest. Forces are balanced. There are two forces. Gravity pulls straight down, mg, and then we have the buoyant force up. And so capital B again is the magnitude of the buoyant force. Next, what I do is I turn this mass term into density of object times the volume of the object. And now I can look at the buoyant force, kind of unpack that a little bit, looking at the subscripts, and then figure it out. So I'll go over here on the left and do that. So the buoyant force, always just write it down without thinking about it. It's just the density of the fluid times the volume of the fluid displaced. We'll ask the question about that in a second, and then times g. All right, now we dig in and we say, what is the volume of the fluid displaced here? Just go ahead and pause the video and think about how we could write that. All right, so right here in the middle, I'm kind of changing my subscripting. The volume of the fluid that is displaced by the object is all of this stuff here that's below the water level. So I'm calling that the volume submerged. So that's all of this. In fact, I'll draw that in here. All right. And then the percent below the fluid, the percent of the volume of the object that is below the fluid, is the volume submerged, so all of this stuff, divided by the volume of the entire object. And that would give you the answer. So we can now continue along over here on the right and plug in for the buoyant force. So we'd get the density of the fluid times the volume submerged. I'll just say sub for submerged, times g, and I'll bring the other term over to the other side. So this becomes the density of the object times the volume of the object times g. I think you can finish it from here. So do some algebra and see what happens, and then we'll get to our result. All right, so you just set them equal, g's cancel out, and if we do simple division, we see that the volume submerged divided by the volume of the object is the ratio of the densities here of the object divided by the fluid density. And plugging in from before, the object has 80% of the fluid density. And so the fluid density terms cancel out. And we have now shown that the percent of the volume below the fluid level is 80%. That means the amount above the fluid level is 20%. If If you've ever seen, obviously you have, a picture of an iceberg, all you really need to know is what the density is um, for the ratio of the densities between the ice and then the ocean, and then you'd be able to figure out how much of the volume of an iceberg is below and then above the surface of fluid. One final thing about these types of problems when you have objects that are partially submerged, floating objects, is sometimes the shapes are simple, and I kind of gave you a shape like this, and if you wanted to, you could, if this was A and then this was H, right, you could start talking about the volume of the object in terms of these other variables, which would be A times H, and that would allow you to figure out the height of an object that's either above or below the water level, um, which is helpful as well. It's really the same physics. It's just at the end of the day, you'd sub in here for um, you know A times H up in here, um, and then you can solve for the ratio of these heights or anything else. All right, so just to wrap it up, all you need to remember for the buoyant force is it's always equal to the density of the fluid times the volume of however much fluid has been displaced by the object times g. When you have a totally submerged object, this subscript here becomes the volume of the object. When you have a partially submerged object, it's just the part of the volume of the object that is submerged is what you can turn this term into there. And paying very close attention to your subscripting when you're writing out the terms for the buoyant force is really important for you to be able to analyze problems just in variables, because those subscripts communicate information, and you can see how when we divide, say, the volume of submerged by the volume of the object, like we just did, that had some conceptual meaning of what percent of the object was below the fluid level. So making sure you have the subscripts correct allows you to do those kind of abstract mathematical steps that then unlock further insight to the problem and when you're not working with numbers. All right, so anyways, I hope that gave you some good insights on the buoyant force, and we'll see you next time.